Good afternoon, ladies and gentlemen. It's a great pleasure for me to be here, and I'd firstly like to acknowledge ARRA for inviting me and for supporting my trip here. So hopefully I will return the favor by making this session worthwhile. I've changed the title slightly, but it's just to clarify the point, and that is the application of cold recycling technology, and in particular bitumen stabilization. There are differences between the northern and southern hemisphere, and the question is, are they surmountable? So that's why I changed it a little bit, with my perspective really coming from down under, not the Australian down under, but down in the south. Now, it seems like your president has forgotten where the continent of Africa is. He never mentions it. I think Trevor Noah has created some waves there, possibly. But just decided to show you a map. So Stellenbosch is right down the southern tip of Africa, near to Cape Town. That might be a city that people are acquainted with. And obviously we are known for our animals, and everybody knows, well, I think most everybody knows the Big Five, which we have in South Africa, not in Stellenbosch though, unfortunately. But the question that always puzzles me is, what about these animals? I mean, we've got the fastest land animal there, we've got the tallest, we've got the cutest, and also, well, the tallest is also the friendliest. I mean, when I get home, I get this greeting. But we've also got other benefits, and as Matt, our first speaker, the keynote speaker, told us that it's important to have a coach if you want to perform, and we have some great African athletes. We have some of the best in the world, middle distance and long distance. However, I wanted, just before we start the presentation, also give a bit of context from a sporting point of view, seen as Matt set the scene with all his motivational explanations. Now, I'm sure one sport he didn't play, somebody, I think Mike Marshall said he had played almost every sport. I can guarantee you he hasn't played cricket. Well, not the way that we play cricket, but it's a really macho game. If you look at the names of the fielders, some of the requirements to play cricket, you've got a square leg and you've got a short leg. These are really sort of macho names that we give our cricketers. And a fine leg. It's also played by ladies. They play a World Cup as well. And we've got a silly mid-on and a silly mid-off and a silly point. But what's the point of all of this? Well, to give perspective on cold recycling, this cricket started in you can see the date down the bottom there, about the 1600s, the game first started. And it was only in 1874 that they decided to equip themselves with some protection, the cricketers. But what I'd like to highlight is that it took 100 years before they decided it would be important to maybe protect your brain as well. And it's a little bit like cold recycling, is that with the start in the technology, it was all about protecting the assets, and that the assets were judged on an economic point of view. It's now that we've got our thinking caps on, and if we look at some of those earlier presentations today, it's fantastic to see the developments in research and implementation of the technology. So briefly, what I would like to cover is some of these bridging the gap issues and these surmountable, I believe, challenges between the different regions. Well, one thing we know for sure is that developing countries, as South Africa is, has a distinctly different pavement structure, typically, to Northern Hemisphere countries like the USA, Canada, and European countries, where there's much thicker asphalt. And there's good load spreading because you have stiffer layers. There's protection of the subgrade, can be a slightly shallower pavement. We know there's protection from moisture. So these are all very nice things. But when it comes to rehabilitating these roads, and the picture on the right-hand side, although it does look like thick asphalt, that's meant to be a granular layer and only a very thin layer on top. And that poses us with a lot of challenges in South Africa because maintenance is key. And it's nice to see the research being done here with thin surfacings too. I'll show you an example of just how well thin surfacings can perform. So in this rehabilitation conundrum, we can consider pavements with thick asphalt surfacings or thick asphalt structural layers and thin asphalt layers. One of the benefits is that this is a great material if it's used properly in the recycled pavement. So I gathered a little bit of information just at some of the challenges, general comments of this technology and its application in the United States. And I must say, that with the benefit of this, I think being my fifth ARRA and AEMA conference that I'm attending, one can see that there are challenges around the design system. There's some fairly simple design systems that are still using like a structural number approach, which is very useful for the first level of design, but not that sophisticated. So one can have a sort of factor as how much you've improved the layer's performance by using bitumen stabilization. Or one can use these structural number approaches where one can improve the structural coefficient of that particular layer. But what that doesn't account for with that sort of approach is what sort of stiffness and load spreading capacity are you building into the pavement, and how does that benefit the surfacing? And there you need to go into some structural mechanics considerations in terms of strains and stresses inside the pavement. And Buzz explained it quite nicely in his presentation in terms of how important that is. The other thing is, and I'll pick this up a little bit later in terms of research, is how does one determine those layer coefficients? And I'm not entirely clear how cold recycling and bitumen stabilized materials are incorporated in MEPDG, and whether they are explicitly incorporated there. Maybe this research will lead to them being incorporated. I'm hoping that's the answer to that question. There is triaxial testing being done to understand the performance properties of these materials, but really in the USA only on a research level, not in full implementation. And then some problems have been solved where FDR and CRR have been treated as two separate materials, where I believe that there's actually it's a sliding scale as you move from FDR into CRR with increasing RAP content. So this is an important thing we need to understand through research. And that basically covers the bullet down below. In some of our early research, we looked at the performance parameters being the shear properties of this bitumen stabilized material. And I use that term generically. Whether it's emulsion or foam bitumen, we use the same evaluation tools, giving an equal footing to both of the technologies. So what one can see here is low RAP contents and higher RAP contents. And subtleties, these were two different emulsions and foam bitumen, that's the EEF. Those two don't have any active filler, and you can see what the active filler does. But what I'm interested in more is between 25% and 75% RAP, one can pick up an influence, a significant influence, on the cohesion values, as well as the influence, which is slightly negative, in using more RAP in terms of the friction angle. These things can be linked directly into the performance of these materials, and that's why triaxial testing is very useful, not just at a research level. The research that we have done is continued also with these 300 or 12-inch by 6-inch diameter specimens and exposing them to pulsing of water at pressures 145 kPa, for example, that can simulate hydrostatic pressures from traffic under saturated conditions. And from that, we've also better understood the response and the performance of these materials. How do they withstand moisture damage? Because that is a concern by many people, and a well-founded concern. We have to address it in terms of how can these materials stand up to wet conditions and wet climates, etc. But we can see certainly there are challenges if we leave out the active filler, and these are also emulsion and foam stabilized materials and different types of aggregate as well. Just part of the research showing how we developed some limits for what is an allowable loss in cohesion from triaxial testing. That's somewhere along the lines of your TSR. What is your relationship with an RTS, wet and dry? Just a few slides on the testing of different RAP percentages. This is now another of our researchers who did his PhD on it. What I found interesting here is that, yes, the RTS value, similar to what Herkelom, the Dutch guy, did in the 1950s, showing how the binder stiffness influences the ultimate strength of the mix for asphalts, but it's binder related. You can see the temperature influence over there, but the RTS is not really differentiating much between a mix that's got 100% virgin aggregate and 100% RAP, and another mix in between, a 50-50. What is also interesting out of this research was the influence of the RAP content on the permeability of the material. And if we notice over here, decreasing the RAP content actually decreases the permeability. And it's all about the voids. These are different mixes over here. You can see, these different types of pre-treatment of the materials. But the point is that the percentage of RAP does influence the permeability of the material. And well, on the right-hand axis, you can see it there, but it appears again here, just focusing in on the voids. Now, this is an interesting aspect of these special materials, and that is even though the voids are pretty high, and for those of you who aren't acquainted with the typical voids that one gets in a foam or emulsion mix of this nature, where we're talking about 2 to 2.5% of bitumen, you'll be quite surprised to see these voids are above 12%. However, many of those voids are not interconnected because of the dispersion of the binder in the mix. And you'll notice on the previous slide that the permeabilities are still pretty low. And that's how these materials present their resistance to permanent deformation, moisture damage. Some other slides now. This is just the same analysis, but now looking at the cohesion of the materials with different percentages of RAP. Again, 100% RAP, 50% RAP, and 0% RAP or 100% virgin aggregate. I would prefer to look at the non-conditioning values over here because this follows the trend of the previous results. And what these results show us is that grading is an exceptionally important consideration. So if we're using 100% RAP or even 50% RAP, the gradation of that RAP and obviously of the blend is extremely important because ultimately it's the voids that are going to influence the permeability. We've done other research as well to try and understand the flexibility of this material. And the one way of doing it is a monotonic beam test with different binder contents, for example, and different active filler contents. And from that, we can measure stress and strain at break, and we can measure dissipated energy and those sorts of things. And what was interesting about this study, we wanted to uncover with emulsions and foam, what is the influence of adding more than 1% of active filler? Because general application of these stabilizing agents of emulsion and foam is trying to restrict the active filler. There are those who believe we should be pushing the active filler a little bit higher because it gives us higher stiffness and strength, but it creates brittleness, as we found from this research. We sort of know it intuitively, but we can see on these two lines, you're going from this is in terms of the stiffness of the material. By adding an extra percent, taking you from 1 to 2% of cement into foam and emulsion mixes, you get a kick in the stiffness. It really does shoot up. But if we drop down, what we found the strain at break to be a more reliable way of giving us an insight into at what strain level did that beam break in terms of a surrogate for the flexibility of the material. And as you can see there, with the original 1% versus as soon as you start adding 2% for the foam and emulsion, we see a significant drop-off in the strain at break. Loss in flexibility. So flexibility is the inverse of how much cement we add to these mixes. And we need to remember that. Just to give you some insight into, again, Southern Hemisphere, but that we're not only doing FDR type work, which has got a smaller percentage of wrap and more granular material blended into it, that we do some 100% wrap projects. This was one that I was involved in with a colleague of mine, Dave Collings, really challenging one. Let me just go back there. So São Paulo on the eastern coast of Brazil, the biggest city there in Brazil, very heavily trafficked highway that is also a concession, and the concessionaire was having headaches about having to maintain an extremely heavy traffic. I'll show you in a minute. So was looking for solutions because mill and replace was lasting 6 months to a year maximum on these roads. And there you can see what the problem is just by this block cracking you see at the top, in combination with 15,000 heavy vehicles per direction per day on this highway. So extremely, that's vehicles. It's not, you've still got to get easels per vehicle, which ranged between 3 to 5 standard axles per vehicle. And the other challenge was working between 10 p.m. and 5 a.m., trying to rehabilitate this road. Mill and replace wasn't working. This is the problem. So set the scenario. You've got 350 millimeters of cracked material. The problem is coming from a cement crushed stone base that's been there for quite a while, well-developed cracks. It was originally treated with 6% cement. Surprise, surprise, it cracked. And it's presenting itself on the surface like this, the block cracking. So the problem's in the base, but it's still got 10 centimeters of asphalt on top. Obviously, you can't mill those 2 layers out and replace with hot mix asphalt in one night. I mean, it's just not going to cool down. And anyway, trying to compact 350 millimeters in lifts in one night is impossible. So the process that we investigated was to mill off the cracked asphalt, the 10 centimeters, mill off the 25 centimeters of granular underneath, keep them in separate stockpiles. And then, as you would have seen there, take those blends of those stockpiles and then compact it back into the box that you've created in that 7-hour window in 2 layers to get the compaction. So 20 centimeters compact, it's paver laid in the box, compacted, overlaid by another layer immediately of 13 centimeters, and then that thin surfacing we were talking about on top. and then go to church and pray. Because at 5 a.m., you're opening it to those 15,000 heavies in that direction. And if you've done anything wrong, it sure as hell is going to show up in the first day. So it challenged us also in terms, the practicalities are one thing. The other thing is designing those layers. How does one design this pavement structurally? We don't really have the tools to do that. What was also planned is that the concessionaire was concerned about this pavement being a bit too thin on top in terms of asphalt. So after trafficking it for a while, after several weeks, they wanted to mill and replace with 50 millimeters of asphalt. Well, these design functions, and this is just coming back to using a structural number approach, there are different, this is where the variability in these layer coefficients come in. And they've all been properly verified. The variability is as a result of differences in the material. And as we heard earlier, there are some fantastically performing BSMs. But this, unfortunately, doesn't really tell us much about the support for the surfacing layer and how's that going to have a reduction in fatigue as a result of improved support. So I believe this was one of the signs put up on one of those trial sections that performed so wonderfully. And that was quite far from the truth, I reckon, that there was risk of sudden catastrophic sinkhole collapse because the road is still there as if it was built yesterday, I believe. Anyway, so the design system that we have gone for, that's formed now part of a mechanistic empirical approach, coming from the Southern Hemisphere, but I'm trying to say I think this is applicable all over, is to analyze what are your stresses in the pavement. Stresses, not strains, with this material because it's got this non-continuously bound nature, a little bit granular. Take those stresses, plot them together with your strength of material. So you can do triaxial tests to get that design envelope. These are your actual stresses over there, the green Moore circle, and the ratio of that Moore circle and the blue one, which is the failure Moore circle. If you look at the deviator stress ratios of the two diameters, that ratio as a percentage is going to indicate to you how quickly the rutting takes place. So at a low deviator stress ratio, if it's 30%, you're going to get some settling in, embedment in the beginning, shakedown, whatever you like to call it, and then it's going to flatten out. There will be increase, slow increase over time. But if you can restrict that deviator stress ratio, you're going to get the right sort of performance and you're going to limit the permanent deformation. So the architecture of this new design function is based on the design traffic, how many axle repetitions the material can handle. The CRR or FDR is a function of the relative density of the material. These are the key variables that have come out of the research. The plastic strain percentage, what is your tolerance in terms of how much permanent deformation is allowed at the terminal condition. The retained cohesion, which comes out of how much cohesion you have remaining in the material after exposure to moisture damage. And then finally, that deviator stress ratio. So those are the four components. And as you can see, that stress ratio is a power function. We've developed that function with coefficients. Now got it 2 days ago from one of my students evaluating the whole final report on it. And this is the type of function that we're using as in that project. And this is the type of output that we get. So just to emphasize the point, we have, and I say we, the industry, has the know-how how to use this type of analysis. You can see that the blends that were used on that Ayrton Senna highway in Brazil were different. One of the reasons was with the extremely high traffic and thin surfacing, we wanted a bit more friction angle in the mix. So the 100% wrap is all part of that well, it was 300 millimeters ultimately in total of bitumen stabilized material. And we can see over here from this analysis, those deviated stress ratios are less than 25%. So this design was put in place to deal with really heavy traffic. We also moderated the stiffnesses that can be achieved in the material. As we can see over there, with the support of 600 MPa on a graded crushed stone, which was the in situ material in that Ayrton Senna highway, we could easily develop the stiffnesses required to carry the traffic. And if one looks at the modular ratios, the ratio and stiffness between two adjacent layers, which is a fact of nature. You can't have an extremely stiff material on an extremely soft material, that plate of glass on the feather bed type of scenario. And this type of balanced design helps to reduce those ratios of stiffnesses, as we can see in the red values. And they meet the requirements of nature, let's say. You will see also that in this type of design, one can explicitly use the material properties that you evaluate for the materials. So here you can see where you have some crusher dust, you get a slightly higher friction angle than the mixes. So it's 41 to 38. It might not seem like much, but that could be the difference between pass and failure in terms of the performance of the material, as well as the cohesion values. So these are measured values, and I'll show you a few in a moment. So in terms of our general guidelines that we use for mechanistic empirical design, you can see the red values depends on what type of supporting layer. That's the subbase, and this is your base layer, your bitumen stabilized material, with wrap and graded crushed stone or more graded crushed stone. So this would be the CRR is heading more in this direction, and there you can see the range of values that we used in the design fit right into that scenario. Some of the values that came out of that particular project, here we can see the resilient modulus values, actual values actually higher. We were conservative going down to 600 megapascals in the design, but rather be on the safe side. This was a dry cure. As you can see, a really humid cure, if you don't allow the moisture to come out, can create entrapped moisture and can reduce the stiffness of the material significantly. In terms of back-calculated resilient moduli, you can see that over time, after construction, even under traffic, so one would expect the traffic to damage the material, but actually the curing dominates the behavior of the bitumen stabilized material. And you can see an increase into well over 1,000 megapascal of stiffness in the material. And this helps us as a benchmark type of project to understand what sort of design limits we should have for future projects. Just a few slides on the project itself. So this would have been taking off the 100 millimeter surfacing, mill, and then take it into the local stockpile. As I mentioned earlier, and I think as has already been mentioned, the gradings are exceptionally important. And single stage crushing with specifically an impact crusher, it works better than a jaw crusher or a cone crusher, which tend to push wrap material together. If you're working with CRR type of material and the in-plant type of process, as in this example, you don't want to create clumps of the material, and you want to get a very smooth, continuous grading. So that's imperative. And then the ability also to blend in the mix that wrap and whatever other components you require, both in terms of either lime or cement and the amount of bitumen. And as you can see, the more wrap you have, the slightly less binder you need in the mix. You can see a difference between 2 and 2.1% of binder. And in a big project, that is significant. This is the second part of the first stage of the operation. So there's the second cut, which is then through the cement treated, that cracked existing base layer, the cement treated base, into a separate stockpile. I've left out, unfortunately, they're all night shots, but the paver laid 2 layers of bitumen stabilized material and compacted, and then the final surfacing and opening to traffic. That was in 2011. This concessionaire, as I said, was really concerned about how to control this problem, and the original trials were in a 500-meter section. This is a couple of years later. Still, you can see the rehabilitated lane is showing no signs of distress. I can happily say I was there 7 months ago, and it's still looking, no, less, 3 months ago, and it's still looking in that condition. But subsequently, the lane alongside has also been rehabilitated now, and we're 6 years into this rehabilitation. The concessionaire has got the contractor so well trained up into it, they're just going section by section and systematically treating the problem. So I think with the right design and the right materials, and obviously the right implementation in terms of the construction, this is the type of solution one can come up with using this technology. And I should just say that ARRA has kindly given me another slot tomorrow to talk a little bit about the mix design procedures, and I'll explain how those specimens are prepared and tested and how that is all evaluated. So, Mr. Chairman, I'd like to conclude in saying that there's a lot more attention being paid on the investigation of these projects, in particularly controlling the grading of the RAP, etc. The mixed design system is available and in place for these materials with much better insight into the performance properties that should be carefully looked at. The design takes into account climatic conditions and critical conditions, curing and exposure to moisture. We have to be real about these things. And the design function will be published. The one that I showed you is an interim one, but the architecture is exactly the same, few minor nuances and changes. And as we can see, I think both processes have their place, and we saw it earlier in terms of the performance in plant in place. Properly implemented, I think, can get the right results. Thank you for your attention, and I'll be happy to take any questions. Yes, John Martin.
So I hope everybody can understand me. So you're looking at this material as an unbound material with a component that allows you to increase cohesion from the bottom to the top. Did I understand that properly?
Yes. Okay, so first part is it's like an unbound material on steroids. I mean, it's just unbound, still got the friction angle, but the cohesion is significantly higher. We're talking about, with an unbound material, you might have 35, 50 kilopascal. Here you've got 250 kilopascal upwards.
That's the cohesion.
Yeah. But then coming back to your other part of the question, those values would not necessarily, on that particular project, they did change from the bottom to the top, but one can also design it in one layer as a uniform cohesion and friction angle.
The reason I'm asking is if the top material was placed right on top of the natural soil,
yeah,
that material would not have the same properties.
Exactly. That's where the modular ratio comes in. You will see that we check the modular ratio. Do you have a realistic stiffness? Because what you're saying is if you've got an existing soil that has an effective stiffness of 100 megapascals, there's no ways you're going to get 600 megapascals or 800 on the next layer above it, particularly with the stress-dependent nature of the material. We talk about 3 times modular ratio, so you will maybe get 300 megapascals. With this project, fortunately, the granular material underneath was a graded crushed stone, so it had a pretty good stiffness to begin with.
So are you working with specific lift thickness to use that ratio?
With a project like this, yes. It's a bit of an exceptional project because you're treating 35 centimeters in one go, but we look at, if you use in-place recycling and you've got a fairly consistent material, you would not have to compact that layer in 2 lifts. You can compact 25 centimeters in 1 lift. Extreme conditions, both traffic and in terms of depth of treatment, led us to compact it in 2 lifts and improve the compaction. Thank you for that question.